space curve. So a vector function R is continuous at A if we basically have the limit is equal to each other. So the limit as t approaches A of R vector of t is equal to R of vector at A. Basically when this is continuous at A if the limit exists. Yeah, I think that's more appropriate. Yeah, because I honestly thought it was a vector, but yeah, basically it's continuous at A if the limit exists. Again, very similar to just normal functions. All right, so in view of definition 1, we see that R is continuous at A if and only if its component functions f, g, and h are continuous at A. So in other words, if it's continuous, if you go definition 1, so if R is continuous at A, then basically all of these limits have to exist, and they all have to equal. They all have to exist. In other words, they all have to be continuous. So they're all going to be have a real number value there. So yes, so the components are as well. There is a close connection between continuous vector functions and space curves. So suppose that f, g, and h are continuous real-valued functions on an interval I. Then the set of all points x, y, z in space where, so if we have basically now we're taking the vector function, basically drawing it in real 3D space. So the x1 is going to be now the x component is going to equal to the I component. So f of t. The y is equal to g of t. And now the z is equal to h of t. So now the actual coordinates in space have are the components of the vector function r. Yeah, and back to this statement. So basically, then the set of all points x, y, z in space where we have these x, y, z equals to the components of the vector, and t varies through the interval I. This is called a space curve, just a curve in space. So the equations above are called parametric equations of C. This is a set. This is a set of all numbers in space where it fits these functions, and t is called the parameter. We can think of C as being traced out by a moving particle whose position at time t is f of t, g of t, and h of t. And if we now consider the vector function r of t is equal to f of t, it has components f of t, g of t, h of t, then r of t is the position vector of the point P, point P is the position vector of it, and the point P is just anywhere on that set, on that space curve. So f of t, g of t, h of t on C. Yeah, so thus any continuous vector function r defines a space curve C that is traced out by the tip of a moving vector r of t as shown in the figure below. So what I mean by that is, let's say we have, this is our xy, this is our y. This is going to be, I'll make this even bigger. So this is our y, this is our z, and this is our x component in space, like that. And now let's say we have a space curve. So we have like this, and it goes like that. It loops underneath, and it goes all the way across like that. Let's erase this part like this. It goes like that. So it goes underneath and loops. And it goes like this, goes up. This is our C. This is a set of all points in the space curve. It loops like that. I'm just drawing it from my calculus book. And it loops like this. It loops around, goes under. Goes like this. And now this point right here is P. So let's say that's just any point P. And this one right here is P. And let's say the point P has coordinates f of t, g of t, h of t. Because it's a parameter, so it can loop around depending on what the value is of function. So it looks like that. And then r is going to be the position vector. It is a curve that C is traced out by the tip of a moving vector. So that moving vector is a position vector that goes all the way to this point P on it. So this is r of t. This is r of t, and this is in vector components, and now we do the triangle brackets. So that's a point, this is a vector. This is direction, length of it. And the magnitude or length is the distance to the point. Like that. So there it is. And this is going to be r of t. This is going to equal to, yeah, the same thing, f of t, g of t. But now it has a square bracket. I mean, yeah, the triangle brackets because it is a vector. The other one's a point. Vector, point. All right, there it is. Epic stuff. And yeah, just put this note right here. C is traced out by the tip of a moving position vector r of t. So that as this moves around, it's going to change and alternate and so on. It's going to be smaller here, bigger, and so on. And then if you just trace the tip of it, that's the curve C. It's just epic stuff. And now let's take a look at example 3. All right, this one states, describe the curve defined by the vector function r of t is equal to 1. Yeah, this has components 1 plus t, 2 plus 5t. And this one, the k1 is a negative 1 plus 6t. Alright, so the solution, so basically the corresponding parametric equations are, so let's write down, I guess we want to describe this in vector 1, so we could do, this is going to be the f of t, g of t, h of t, or just, we'll just write it as our x component, because we're going to draw this in 3D space. This is going to be our x, 1 plus, this is the x component is just going to be x is equals to 1 plus t. Write this a bit neater. And then the next one is y is equal to 2 plus t. And then the z is equal to negative 1 plus 6t. And now these parametric equations which we recognize from my earlier video as parametric equations of a line, is linked to my earlier video. Basically parametric equations of a line passing through the point 1, 2, negative 1. You get the 1 from here, 1, 2, negative 1, and parallel to the vector 1, 5, 6. And that's going to be the direction of the constant in front of the t. So, and this one is 1, 5, 6. And again, just recall from my earlier video, here's the thumbnail of the sections of it. So parametric equations of a line. So if you have a line L, then you have R, you have the position vector, or the R naught is this point on it. And then this one right here, this is the direction vector. That's the A component, and that's parallel to this one right here. This is our V. Yeah, so A is parallel to this one. So yeah, this is going to be R is equal to, yeah, R naught plus A vector, which is parallel to this one. The same thing as just writing R naught plus T times V. Yeah, because this is parallel to it, but this is longer. So then you times it by a parameter T like that. I'm just refreshing my own sake. So this is going to be the point on this x, y, z on the point P. And now what we end up having is, yes, we have this component is x naught plus, x naught, y naught, z naught plus t times it by a, b, c. And again, that's just the directions. This is parallel to this one right here. To get the same length, you just have to multiply it by parameter t. And what I mean by the same length is, this just changes. As you change this, you're going to have this one changing. So it's going to go all the way across, or yeah, smaller or bigger, depending on what the value is. So in other words, it's a point on it. So if you have a really big t, positive, it goes all the way. So your point P is going to go over there. Your R is going to shift all the way there. So again, it's just these are just parametric equations of a line. And again, that point on it, this one is through the point. This one's just the this x naught, y naught, and z naught. So that's going to be our 1, 2, and negative 1. In this case, it's going to be our x naught, yeah, y naught, and the other one is the a, b, c. So a is 1, b is 5, c is 6. Yeah, so there is that one. There's the components, and split them up inside here because you can add these up. Anyways, so alternatively, we could observe that the function can be written as r equals to r naught plus tv. So again, that's exactly what it is. Yeah, where basically r naught is equal to 1, 2, negative 1, and v is equals 1, 5, 6. And this is a vector equation of a line that's given by the above image and my earlier video. There's your earlier video on it. And again, it's just they're all the same thing. You could write it as parametric equations like this. So you could write these as parametric equations like that, or you could just split this up into its component, a vector equation of a line. So r equals r naught plus t times v, where, yeah, when you have t times v, this one just equals to, well, tv, whatever parameter it is at that point. So anyways, that's all that is.